final bit of the theory in this chapter of torque and angular momentum, Newton's laws, how to build the Newton's laws for system of particle. For a particle, Newton's second law is defined as the net force is equal to rate of change of linear momentum. And for turning of the particle about a reference point, the net torque acting on the particle about that point is equal to rate of change of angular momentum of that particle about that fixed point. For the system of particle, we know that tau, the net torque about any point, reference point, ith particle, velocity vi, mass is mi, is given as Ri cross Fi. Fi is the net force acting on ith particle. If you take the center of mass somewhere here, Ri can be written as RIC plus RC. Ri can be written as RIC plus RC. Then you can write the net torque about this point as RIC plus RC cross Fi and summation of this. RIC cross Fi, summation of this plus RC cross Fi, summation of this. This is the net torque about O. This is the net force acting on ith particle. This is the position vector of ith particle with respect to the center of mass frame. Therefore, this is the torque experienced by the system due to the all forces about the center of mass frame. I write it tau c plus RC is a constant quantity. You pull it out, cross, you take this symbol of summation sigma inside, and this physically signifies the net force acting on ith particle. So tau c plus RC cross, this is the net force acting on the system, which is equal to sum of the net forces acting on all the particles. I call it F. Let it be F net. That is equal to the net torque acting on the system about the given reference point. This theory previously we deduced. And we have the similar type of expression for the angular momentum, which states that angular momentum about the point O is equal to angular momentum about C plus angular momentum of the center of mass about that given reference point RC cross M into VC. This is equation number 1. Since angular momentum about O is equal to angular momentum about the center of mass plus angular momentum of the center of mass with respect to the given reference point. Taking the derivative of both sides, we can write the rate of change of angular momentum of the system with respect to the given reference point is equal to rate of change of angular momentum of the system with respect to the center of mass frame plus rate of change of angular momentum of the center of mass of the system with respect to the given reference point O. That is equal to dLc by dt derivative of this term, that is drc on dt cross mvc plus rc cross d by dt over mvc. Since this is equal to vc and vc cross vc is 0, the entire term will vanish. Then we are left behind with these two terms, rate of change of angular momentum of the system with respect to center of mass frame plus RC cross rate of change of linear momentum of the center of mass is none other than the net force acting on the system, supposed to be acting at the center of mass. That is equal to rate of change of angular momentum of the system with respect to the given reference point. This is equation number B. Since torque is equal to rate of change of angular momentum for any reference point, we can write tau O equal to d by dt of LO. Tau C is equal to d upon dt of LC. Then writing tau is equal to tau C plus RC cross F net force is equal to d LO upon dt is equal to dLc upon dt plus RC cross F net, and this factor is none other than the tau C. Or you can just compare these two terms and compare these two terms to get a pair of equations. Comparing both sides, we have tau C is equal to rate of change of angular momentum above the center of mass. This is one equation, and comparing these two, RC will be common, and we are getting the net force acting on the system is equal to rate of change of the linear momentum of the system. F net is nothing but m into AC, mvc is equal to m dvc upon dt. That's equal to m into AC. Therefore, we are getting two sets of equations. F net is equal to total mass times the acceleration of the center of mass. This is called Newton's second law of rotation. This is called Newton's second law of, or for translation. And combining these two will give us Newton's laws for system of particles. For motion of system of particles, there are two types of motion, rotation and translation. When you call rotation, you should see whether the center of mass is moving or not. If you say rotation, you should see whether the system will possess a non-zero angular momentum with respect to the center of mass or not. Now we have put all the equations, all these ideas, the theoretical details of the system of particles, both rotation and translation. And to understand all these ideas, let us supplement through some problems as concluding examples. The Newton's second law of rotation states that the net torque or net torque of all external forces taken with respect to the center of mass is equal to rate of change of angular momentum with respect to center of mass. This is called Newton's law of rotation. And Newton's law of translation states that the net force or sum of all external forces, because sum of internal forces will be equal to 0, is equal to rate of change of linear momentum of the system, that is equal to mass of the system into velocity of the center of mass, or we can just write mass of the system into the acceleration of the system. Acceleration of which point of the system? Acceleration of center of mass of the system. This is called Newton's second law for translation of the system of particles. Well, let us take some examples. Let us project a particle with velocity v naught at an angle of theta naught with respect to horizontal. In gravity, it will move in a projectile path, a parabolic path, which is parabolic in nature. We need to calculate the angular momentum of the particle as the function of time and angular momentum of the particle as a function of x distance with respect to the point of projection. In one method, we can proceed by using the equation torque is equal to rate of change of angular momentum about any reference point, where angular momentum of the particle at time t can be written as L naught or L, angular momentum of the particle at time t. The net force acting on the particle is mg. Since the torque acting on the particle about O due to gravity is equal to mj into this x distance, because this is r vector, this is mg vector, r cross mg, let it be phi. So this angle is, say this is theta, phi by 2 plus phi. R cross mg is equal to r mj, the sine of the angle between r vector and mg vector, and the angle between these two vectors is equal to pi by 2 plus phi. That's equal to cos phi multiplied with rmg. But we know that r cos phi is equal to x, mg into x, and direction wise r cross mg, clockwise or in minus k cap direction, or directly you can just write mj into the perpendicular distance from the reference point onto the line of action, and direction is minus k cap. Equation number 2. Substituting tau from equation 2 in equation 1, we get minus mg x k cap is equal to rate of change of angular momentum of the particle with respect to O. This gives us dLO is equal to minus mg k cap x dt. Let us integrate both sides. dLO integration of this is equal to minus mg k cap vector x dt. We know that the horizontal component of the velocity, of this particle remains conserved, because there is no force acting along the horizontal direction, assuming no air resistance or any viscous force. Therefore, x is equal to v naught cos theta naught into t. Substitute here. This will give us mg k cap v naught cos theta naught into t dt. At time t equal to 0, the angular momentum will be 0, because the particle was here. When the particle is here, the r vector or the x vector is 0 with respect to this point. Therefore, the angular momentum becomes 0. When the particle comes to this position, having the velocity v, its angular momentum let be L. So, L vector is equal to minus mg k cap v naught cos theta naught t dt integral 0 to t. This gives us minus mg v naught cos theta naught into t square upon 2 into k cap. Answer. This is the angular momentum of the particle as a function of time. And if you substitute v naught cos theta naught into t as x, we can get mg v naught cos theta naught, and instead of t you can put x upon v naught cos theta naught square by 2, or we are getting minus mj x square k cap upon to v naught cos theta naught. So, angular momentum about this point of this particle in terms of t is minus mg v naught cos theta naught t square by 2 in minus k cap direction or clockwise direction. And as the function of x distance, it will be minus mj x square by 2 upon v naught cos theta naught k cap, or in negative z direction, or it is clockwise, or it is inward. In this way you can understand that angular momentum is directly proportional to the square of the time, also directly proportional to the square of the x distance. That is the idea. Let us take another example. You take the sun planet case. This is the sun, this is the planet. The maximum distance is b and the minimum distance is a. Let us calculate. Here velocity v1, here velocity v2. Let us find the ratio of velocities, ratio of accelerations, ratio of kinetic energies, ratio of gravitational potential energy of the planet at these 2 points, and ratio of forces, and the ratio of angular momenta, ratio of linear momentum. Let us assume that here the velocity is v1, here velocity is v2. Ratio of the velocities. The starting point is based upon the conservation of angular momentum principle. Since net torque is 0 as I explained, angular momentum of the planet can be conserved. So, angular momentum at this point 1 is equal to angular momentum of the planet at this point 2. Here angular momentum is m v1 into a. Here angular momentum is m v2 into b. It's getting cancelled. v1 upon v2 is equal to b upon a. Answer. For acceleration, Here the force acting is F1. Here the force acting is F2 due to the sun. So acceleration 1 at point 1 upon the acceleration at point 2 is equal to F1 by m upon F2 by m. According to Newton's second law, we are getting the ratio of the forces. And here the forces J, let us assume that small m and capital M are the masses of the planet and the sun respectively. So F1 can be written as gmm by a square and F2 is gmm by b square according to the law of universal gravitation of Newton. So these two will get cancelled. You are getting b square upon a square. Answer. The kinetic energy ratio is equal to half m1 v1 square upon half m2 v2 square. But these two masses are equal. So it is just v1 upon v2 square of this. But v1 upon v2 is equal to how much? b by a square. Answer. And potential energy E1 upon U2. The expression for the potential energy of interaction between two masses in gravity is given as gm1 m2 by r square. Here m1 m2 is small m into capital M and r is for this position A, and here for this position the r is B. In this way, if you get cancelled, this numerator term g small m into capital M, you are getting b square upon a square. Answer. Now let us calculate the force. As we know, the force is directly proportional to the product of the masses and inversely proportional to the distance of separation between the sun and the planet. Therefore, F1 by F2 is equal to gmm by a square by gmm by b square is equal to b square upon a square. Answer. Come to the angular momentum. Since angular momentum at 1 and 2 are equal, L1 upon L2 will be equal to 1:1. And linear momentum, P1 upon P2 is equal to mv1 upon mv2. So mm getting cancelled and you are getting v1 upon v2, that's equal to a b by a as you calculated earlier. The central concept is conservation of angular momentum. For this example,